of molecules can be classified according to their moments of inertia. They are typically represented by a 3x3 inertia tensor. The rotational motions of polyatomic molecules in 3 dimensions are different from diatomic molecules. A molecule has 3 principal axes of rotation which pass through the center of mass and are orthogonal to each other. The 3 principal moments of inertia are referred as IA, IB, and IC, which determine the rotational energies of polyatomic molecules. The polyatomic molecules are classified as linear molecules, symmetry top molecules, spherical top molecules, asymmetric molecules based on their moment of inertia. Linear molecules, the examples are the example is given as carbon oxysulfide. Symmetry top molecule, we have 2 kinds. Prolate symmetric top molecule, examples are CH3Cl, CH3F. Methyl chloride. Oblate symmetric top molecules are boron chloride, ammonia. Spherical top molecules, methane. Asymmetric molecules, the example will be water and phenyl. The rotational property of any molecule is expressed in terms of moment of inertia about 3 perpendicular axes. The moment of inertia associated with the 3 axes are referred as IA, IB, and IC. The rotation along the bond axis is termed as IA, about the x-axis. So it rotates about the x-axis. End over end rotation in the plane is denoted as IB, and this is about y-axis. End over end perpendicular to the plane is referred as IC. This is rotation about the z-axis. Now we will look into the linear molecules. Atoms are arranged in a straight line with the bond angle 180 degrees. Here IA equals 0, IB equals IC. The examples are hydrogen chloride, HCl, CO2, CS2, carbon oxysulfide, and so on. And here is the picture of hydrogen chloride, and we have IA, which refers the moment of inertia along A, IB, moment of inertia along B, IC, the moment of inertia along C. Now the mark is given as red, which is center of mass, which is closer to chlorine because it is heavier. And here the principal axis with 0 moment of inertia, that is IA is equal to 0. The center of mass lies nearer to the heavier chlorine atom marked as red color. The axes pass through the center of mass of the molecule and lie perpendicular to each other. Linear diatomic molecules can also be treated similar to the diatomics. Since IA equals 0, IB equals IC for diatomic molecules, the energy levels EJ are given by a formula identical to that of diatomics. The selection rule is del J equals plus or minus 1, and the frequency of J to J plus 1 transition is given by this equation 1.49, where J goes from 0, 1, 2, ... The moment of inertia for the end-to-end rotation of the linear molecule will considerably be greater than that of a diatomic molecule, whereas B will be much smaller. For diatomics, the rotation constant will be around 10 cm/-1, while for the linear triatomic molecule, B will be around 1 cm/-1. So this will be very less. We consider carbon oxysulfide, that is OCS, in which all the atoms lie on a straight line. This type of linear molecule gives rise to a particular simple spectra in the microwave region. The spectrum will show the same 2B separation modified by the distortion constant. For the sake of simplicity, consider the gaseous linear molecule OCS, for which we determine the two bond distances OC and CS. So we are going to determine the bond length between OC and CS. This can be done by isotopic substitution method. Consider first the molecule O16 C12 S32, and here it is given, and P is nothing but the axis of rotation, which is nothing but center of mass, and the distance between carbon and the center of mass is nothing but R1. The distance between oxygen and the center of mass is nothing but R2. The distance between O and C is given as RCO. So obviously it is clear, it is seen that R2 equals RCO plus R1. And when you go for the right hand side, the distance between P and S is given as R3. The distance between C and S, that is the bond length between C and S, is given as RCS. And it's very clear that R3, which is equal to RCS minus R1. That is RCS equal to R3 plus R1. The rotation of O16 C12 S32 molecule is about an axis of rotation passing through its center of mass. Since the center of mass is at P, using the law of balance, which is given as mcr1, where mc is nothing but mass of the carbon, mcr1 plus m0 is nothing but mass of the oxygen. So m0 r2, which is equal to ms r3, mass of the sulfur. The moment of inertia is given by I equals sigma mr squared. So I equals mc r1 squared plus m0 r2 squared plus m3 r3 squared. From the figure, it is seen that r2 equals r0 plus r1, and similarly r3 equals rcs minus r1. And here RCO and RCS are the two interatomic distances which we are going to determine. Substituting equation 1.52 in equation 1.50, we have mcr1 plus m0. Instead of r2, you substitute rco plus r1, which is equal to ms r3, instead of r3, rcs minus r1. And separate mc plus m0 plus ms times r1. Just take common r1 out. We will have this equation 1.54. You bring m0 rco to right hand side, we will have minus m0 rco. And we know that mc plus m0 plus ms is nothing but the mass of the OCS molecule, which is nothing but capital M. So substitute here. So we will have mr1, which is equal to ms rcs minus m0 rco. And therefore R1 equals ms rcs minus m0 rco divided by capital M. Substituting equation 1.52 in equation 1.51. So this is equation 1.52. In 1.51 we have, this is equation 1.51. This is equation 1.52. You substitute here. So we'll have the expression for moment of inertia, which is equal to mc r1 square plus m0 instead of r2 square, you substitute rco plus r1 whole squared plus ms r3 squared, you substitute rcs minus r1. So now substituting equation 1.56 in equation 1.57 for the expression of r1 and simplifying, we will have this expression, which is equation 1.58. So equation 1.58 contains the unknown RCO and RCS. So the moment of inertia is written in terms of RCO and RCS. So there are two unknown bond lengths, RCO and RCS. Now we make an important assumption that isotopic substitution does not alter the interatomic distance. We know already. So applying this assumption to the isotope of carbon oxide sulfide, which is given as O18 C12 S32 molecule, we obtain a similar expression moment of inertia I dash of this molecule, which is given by this. Here we have considered RCO as R dash CO because the bond length will never change with the substitution of isotopes. We know already. So we cannot written here R dash CO and R dash CS. We have written as it is. Whereas for M0 value it changes. So M0 is changed with the isotopic mass. Thus we can obtain both I and I dash from the microwave spectra of ordinary molecule and the isotope molecule. From these moments of inertia, the unknown RCO and RCS can be determined. So I and I dash can be taken from the spectrum. Whereas RCO and RCS that can be written in terms of two equations. So these two unknown equations can be obtained easily. Now we can solve for RCO and RCS provided we have extracted a value for I dash from the microwave spectrum of the isotopic molecule. Note that we need not write R dash CO since we assume that bond length is unaltered by isotopic substitution. Similarly, one can also use the other isotope, sulfur isotope. So instead of O16, C12, S32, we can write this as S34, the isotope of sulfur, which can be inserted and the corresponding bond length also can be determined. The extension of the above discussion to molecules with more than 3 atoms is straightforward. The microwave studies have led to very precise determinations of many bond lengths in such molecules. Molecules like OCS have 2 bond lengths to determine, but there is only one moment of inertia. The problem is solved by taking another isotopic form, which provides us with another equation to solve for the 2 unknowns. If we assume that bond length is not altered by isotopic substitution, we can solve simultaneous equations for these bond lengths. That is nothing but RCO and RCS. Rotational spectra of linear polyatomic molecules. Let us first consider the different classes of molecules, their quantized energy levels, selection rules, and rotational spectra. The diatomic molecules show rotational spectra in which the lines are equally spaced and the rotational constant B can be extracted from the spacings. This allows us to calculate the moment of inertia and subsequently the bond distance. Exactly the same energy level expression and the selection rules hold good for linear polyatomic molecules. Thus, for diatomic, that is, and other linear polyatomic molecules, Ia equals 0, Ib equals Ic, these are the conditions, and linear molecules have only 2 rotational degrees of freedom and all other molecules have 3. We are going to look into. In general, the rotation energy is contained in 3 dimensions, that is, E rotation equal to Ea plus Eb plus Ec. And of course, Ea is given as L squared A by 2Ia and Eb is expressed as L squared B divided by 2Ib. And similarly, Ec is given as L squared C divided by 2Ic. But for linear molecule, Ia equal to 0 and Ib equals Ic. So which implies that La equals Ia omega, which also 0. So this first term will become 0. So equation 1.60 becomes E rotation, which is equal to LB square divided by 2IB plus LC square divided by 2IC, which is equal to LB square plus LC square divided by 2IB. The total angular momentum squared is equal to the sum of its components. That is L squared equals LA square plus LB square plus LC square, and of course we know that LA equals 0, so which is equivalent to LB square plus LC square. So therefore equation 1.61 becomes, so E rotation equal to, instead of LB square plus LC square, we can write this as L square. So L square divided by 2IB, which is equal to L square divided by 2I. So we have kept as IB, which is equal to IC, which is equal to I. This is the expression. We have already seen this expression for diatomic molecules. We have seen that the energy levels are quantized and the allowed energy levels are Ej, which is equal to J times J plus 1 H square divided by 2Y, which is equal to Bj times J plus 1. For polyatomic linear molecules, everything else is the same except for the following. The masses are larger and so are the moments of inertia. Here the rotational constants are smaller, which is around 1 centimeter per minus 1 for polyatomic molecules as compared to diatomic molecules, so which is around 10 centimeter per minus 1. However, the selection rules remain the same. Only those molecules which possess permanent dipole moments are microwave active. Thus, molecules like ethane and carbon dioxide are microwave inactive, while molecules lacking a center of symmetry such as HCN, OCS are microwave inactive. The selection rule del J equals plus or minus 1, S are microwave active. The selection rule del J, which is equal to plus or minus 1, is also the same, and this means that the rotational spectrum consists of equally spaced lines, but the spacing is smaller because of the smaller rotational constants. Now we'll go into type 2. So type 2 goes with spherical, and we have prolate and oblate, and we have asymmetrical. So this is the first figure says about a spherical symmetry, and the moment of inertia which is along A is given as IA, and here it is in spherical symmetry, and all the three perpendicular axes the moment of inertia is the same. So we have IA which is equal to IB which is equal to IC. So for any spherical symmetry, we have A equals A, all the three directions. Whereas in prolate spherical symmetry, we have IA along A is greater than that of IB and IC, but IB and IC are equal. So IA is greater than that of IB, which is equal to IC. Since it is greater, the shape is nothing but prolate shape. It's like a rugby ball. And here IA is lesser than that of IB and IC, and IB and IC are equal. So IA is less than that of IB, which is equal to IC, and the shape is nothing but oblate spheroid. So here A is less than B, but here it is A is greater than B, whereas here A equals B equals C. So what we call this as A equals A. So spherical top molecules, as I said, here IA which is equal to IB which is equal to IC. The example for spherical top molecules are called methane. So we have CH4. So the mutually perpendicular moment of inertia which are the same, which are equal. The three moment of inertia are the same. Molecules have regular geometry, that is tetrahedral, octahedral, hexahedral, and so on. Some examples are methane, CCl4, P4, SF6, UF6, and so on. For these molecules, all the three directions are equal, that is IA equals IB equals IC. So LA equals LB equals LC. The rotational energy is given by this expression, LA squared by 2IA plus LB squared by 2IB plus LC squared by 2IC, which is equal to L squared divided by 2IA. And the figure exactly, the structure is exactly like this. There will be no change in dipole. We cannot study its structures using microwave techniques. Microwave is inactive in this molecule. The quantization condition applied to this equation yields the allowed energy levels, which is given by Ej, which is equal to h squared divided by 2IA j times j plus 1. So instead of h squared divided by 2IA, we can write this as A. So we have A times j into j plus 1. Since the three directions are equal, which is equal to A equals B equals C, we could have equivalently written equation 1.65 in terms of B and C. Instead of A, you can substitute B. Instead of B, you can write this as C. However, by convention, we always start with alphabetic order. So that's why we have written in terms of A. However, since these molecules have zero dipole moment, they are microwave inactive molecules. Now we'll go for symmetric top molecules. So as we discussed, there are two types in symmetric top molecules. One is polarite symmetric top molecules. Then another one is oblate symmetric top molecules. The condition goes like this. Here, IB which is equal to IC greater than IA. Whereas in this oblate molecule, IA which is equal to IB which is less than IC. So here we have one moment of inertia which is nothing but IB which is equal to IC. And we have another moment of inertia which is IA. So we have two moments of inertia, and here too we have two moment of inertia, different moment of inertia. Since we have two different of inertia, what we call this as degenerate case. So one is unique axis, the moment of inertia in the unique axis. Then another one will be two rotational axes. So there will be two directions. There will be two selection rules, which we are going to discuss later. So two rotational axes with the same inertia, what we call this as degenerate axis. One unique axis with a different inertia. In the first case, in polarite symmetric top molecules, the unique axis with a different inertia will be less than that of degenerate case. Whereas in the oblate symmetric top molecule case, two rotational axes with the same inertia will be less than that of one unique axis with a different inertia. The examples are given as CH3F, CH3Cl, methyl chloride, methyl bromide, CH3I, CH3Cn. The examples of oblate symmetric top molecules are given as BCl3, ammonia, XCF4. And this is your center of mass. The red color marked as the center of mass. Here too is the center of mass. And look over here, we have IA. A is larger than that of B and C. B and C are equal, whereas A is larger. And since A is larger, the moment of inertia here it will be very larger. So IA is greater than that of IB, which is equal to IC. The corresponding structure is given as right hand side. So IA and IB, they are mutually perpendicular moment of inertia, which is shown here. Consider a molecule such as methyl fluoride. The three hydrogen atoms are bonded tetrahedrally to the carbon. The unique axis has a lower moment of inertia than the degenerate case in this case. Here, IB, which is equal to IC, greater than that of IA. The center of mass is marked as red. Three mutually perpendicular axes passing through the center of mass. The moment of inertia along the principal axis, which is nothing but IA, will have smaller than the other two moment of inertia. It involves rotation of three lighter hydrogen atoms. If we map out the rotational constant B in space, it will have a rugby ball shape. For symmetric tops, there are two independent moment of inertia, and therefore there are two directions of rotations in which the molecule might absorb or emit energies. They are the rotation about the top axis or the molecular symmetry axis, and the other one in the direction perpendicular to the axis. Considering CH3F molecule, this is nothing but a polarite one. The CF bond is its molecular symmetry axis. Consequently, we need to have two quantum numbers to describe the degrees of rotation, one for IA, another one for IB or IC. So we need to have two selection rules. For rigid polarite symmetric top molecules, the solution of Schrodinger equation gives the energy levels as h square divided by 8 pi square IB j times j plus 1 plus h square divided by 8 pi square IA minus h square divided by 8 pi square IB times k squared in terms of joules. So k is the another selection rule. J is the another selection rule. J into j plus 1. and one can get the number, the wave number as Ejk divided by Hc, which is equal to B times J into J plus 1 plus A minus B K squared centimeter power minus 1 for prolate case, and Bj times J plus 1 plus C minus B K squared for oblate case. Here the rotational constants A, B, C are given as equation 1.69, where J equals 0, 1, 2, 3. This is one total quantum number, rotational quantum number, and K equals 0 plus or minus 1 plus or minus 2 plus or minus 3 dot 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 plus or minus J. So which is nothing but angular momentum about top axis. Here it is CF bond axis. So we have now two quantum numbers. One is J, another one is K. Strictly, K depends on J. For example, if J equal to 2, then K will have the value 0 plus or minus 1 plus or minus 2. Here plus sign stands for clockwise direction, top axis, and minus sign stands for anti-clockwise direction. Two quantum numbers to describe degrees of rotation, one for IA and another one for IB or IC. The total angular momentum J is the sum of separate angular momentum about the two different axes. IA is less than IB, which is equal to IC, and this is for one quantum number IA, and IB equals IC, this is for another quantum number. For prolate, the condition is IB is greater than IA and B is less than A, and A minus B times K squared. So this will have always positive value. Oblate case, IB is less than IC, so B is greater than C, C minus B times K squared, and this will have negative value. Suppose we want to calculate the difference of wave number, then we will have J plus 1 to J plus 2. Then we will have B times J plus 1, J plus 2 plus A minus B K squared minus B times J plus 1 plus A minus B K squared. And this plus sign, and here you have minus sign here. See, minus multiplied by plus, then give minus sign, and this term will get cancelled. We have remaining term. You pull B J plus 1 out, so we will have J plus 2 remaining from the first term, and here you have J. This J and this J will get cancelled. We have 2 times, so 2 times B J plus 1, which is measured in terms of 10 to the power minus 1. As the spectrum is independent of K, hence the rotational changes about the symmetry axis do not give rise to a rotational spectrum. The reason is that the rotational about the symmetry axis does not change the dipole moment perpendicular to the axis, which always remains 0, and hence the rotation cannot interact with the radiation. So equation 1.71 shows the spectrum is just the same as that for a linear molecule, and that only one moment of inertia exists, which is nothing but end over end rotation, which can be measured. In prolate symmetry molecules, which are characterized by IB, which is less than IB, which is equal to IC, and another condition is A greater than B, which is equal to C. And this is the structure of methyl fluoride. All the 3H bond will rotate about when it is rotated like a top. The expression for the rotation energy is given by E rotation, which is equal to EA plus EB plus EC, which are given by this expression. And of course, we know that here LB plus LB plus E, which is equal to LC. So we can write this as LA square divided by 2IA plus LB square plus LC square, which can be replaced by L square minus LA square, because L square equal to LA square plus LB square plus LC square. We know that the total rotational angular momentum is quantized, and its components is one of the directions is also quantized. So the rule goes like this. You have L square phi rotation, which is equal to J into J plus 1 H squared phi rotation. That is, the eigenvalue of L squared is given as J into J plus 1 H squared. Similarly, Lc which operates on phi rotation, which is equal to the eigenvalue is nothing but mjh phi rotation. So we introduce the another quantum number k, which has the same meaning as mj, but the quantization is with respect to the internal axis. And the total value is nothing but for mj, which is nothing but 2j plus 1 values of k. Thus, we may also add to equation 1.75 as La operator operates on phi rotation will give us kh phi rotation, where k equals 0 plus or minus 1 plus or minus 2 up to plus or minus j. The internal axis is fixed on the molecule and the energy depends on k. Substituting equation 1.74 and 1.76 in equation 1.72. So it's given us, so we have 1.74, we have 1.76, and we are going to substitute these two equations here in 1.72. So we have E rotation, which is equal to La squared by 2Ia plus L squared minus L squared A divided by 2Ib, which is equal to, so instead of this, you can substitute k squared h squared divided by 2Ia. And L squared minus L squared can be written as j times j plus 1 h squared minus h squared k squared h squared divided by 2Ib. Taking k squared common out. So out of these two expressions, taking k squared out, we have k squared times h squared divided by 2Ia from the first term, and from the second term we have minus h squared divided by 2Ib, and the remaining term will be j into j plus 1 h squared divided by 2Ib. Now, E rotation can be simplified as k squared. This can be written as A minus B, where A is expressed as this, B is expressed as this. So we have k squared A minus B plus, and of course we know that this is expressed as B times j into j plus 1. This expression is similar to that of a linear molecule, but with an additional term depending on k. All levels are displaced by an amount dependent on k square. Thus, each level is split into j plus 1 levels. Since for a polarity of molecule, A is greater than B, this implies that each level is shifted up by an amount proportional to k square. It is noted that energy depends on k square, so that it is immaterial whether the top spins clockwise or anti-clockwise. The energy is the same for a given angular momentum. For all the values of k which is greater than 0, therefore the rotation energy levels are doubly degenerate. The selection rules for this molecule may be shown to be del J, which is equal to plus or minus 1, and del K equals 0. And here are the energy levels and the transition for rigid correlate right hand side, and left hand side is rigid oblate rotators. And these are the values of J, and these are the values for K. For example, when J equals 0 and K becomes 0. When J equals 1, K will be 0 plus or minus 1. So plus stands for clockwise and minus stands for anti-clockwise. So here it is 0 and 1. For J equals 2, we have three values 0, 1, 2. For J equal to 3, we have four values 0, 1, 2 and 3 and goes on. And of course, J can jump from one step up, one step down, because del J equals plus or minus 1, whereas del K equals 0. So the transition level will be 0 to 0. So this is referred as this line, 0 to 0. And what about the second one? So here it is 0 to 0, and here it is 0 to 1. Again, your del K becomes 0. See, here also del K equals 0. What of this one? 0 to 0, and here it is 1 to 1, here it is 2 to 2. So all the transition will take place with the selection rule del K equals 0. And this is for the prolate case. And this is for rigid oblate case. We have anti-clockwise, but this level we have written as below. See here, we have J equal to 0, we have K equals 0. Whereas when J equals 1, we have two levels. It is written as below. See 0, 1. And here we have j equal to 2. We have k equals 0, 1, 2. So we have done just below. So 0, 1, 2. What is the transition? Again the same del k equals 0. That rule that we are going to apply. So it goes from 0 to 0, 1 to 1. Again del k becomes 0. Del k equals 0. So here it is, see here 0 to 0. We have 1 to 1. And here it is 0 to 0 and 2 to 2. So figure A shows the schematic representation of energy levels and transition for the rigid prolate. And figure B shows the schematic representation of energy levels and transition for the rigid oblate rotors. In prolate, the energy increases as K increases, whereas in the oblate case, the energy decreases as K decreases. That's why written as below. K is drawn as below. The selection rules are del J equals plus or minus 1 and del K equals 0. The del K equal to 0 selection rules ensures that the microwave spectrum consists of equally spaced lines similar to linear molecules. The only difference is that each line here is actually a set of J plus 1 transitions of the same energy. And this is the oblate. Next one is oblate molecule. And as we discussed, and here it is IA is smaller than that of IB, which is equal to IC. So A is smaller than that of B. B is equal to C. And the example is nothing but ammonia, NH3. And IB and IC are perpendicular to each other. The moment of inertia. The degenerate axis has a lower moment of inertia than the unique axis. Here IA equals IB less than IC. The center of mass is marked as red. Three mutually perpendicular axes passing through the center of mass. The moment of inertia along the principal axis IC will have greater moment of inertia than the other two moment of inertia. Considering methane molecule, which is nothing but oblate case, we need two quantum numbers to describe the degrees of rotation, namely one for IA, then another one for IB or IC. So as usual, we will have two quantum numbers. So it involves rotation of 3 hydrogen atoms. If we map out the rotational constant B in space, it will have oval shape. And this is a structure for NH3. For oblate top molecules, IA which is equal to IB less than IC, that is A equals B greater than C, the expression for the rotational energy is given as. This is exactly similar to equation 1.78, which is equal to E rotation, which is equal to K square times C minus B plus J into J plus 1. Since C minus B is negative, each level will be lowered by an amount proportional to K square. So that's why we written as lower level, just below. But because del K equal to 0, the same selection rule, the spacing will remain 2B. But each peak will consist of J plus 1 superimposed lines. For example, boron trichloride. So boron trichloride is given as, the structure is given as exactly like this. So we have oblate top molecule, IB which is equal to IC less than IA. In oblate molecule, there exists an axial rotation and a perpendicular rotation. That's why we need two quantum numbers. So as the last one is asymmetric top molecule, in which we have IA which is not equal to IB, which is not equal to IC. So the moment of inertia are not equal. The example is H2O or phenyl. Asymmetric molecules, the three moment of inertia are different. For that, IC is greater than IB, which is equal to IA. IC is greater than IB, greater than IA. Examples are given as H2O, HCHO, CH3OH, CH2CHCl, C2H2F2. Asymmetric top molecules are the last symmetric class of molecules and are characterized by different moments of inertia IA not equal to IB not equal to IC. Each molecule and spectrum will be treated as separate case. Their spectra are the most difficult to interpret. It's very difficult to interpret. For example, water, C2H2F2, CH3OH, and so on. Their rotational spectra are very complex, but most molecules can be classified as either near correlate or near oblate. Reduction in symmetry removes the plus or minus k degeneracy, and each rotational j level is split into 2j plus 1 levels corresponding to different k. We have seen that rotation energy depends on the j quantum number, but each has a degeneracy of 2j plus 1. When an external field is applied, this degeneracy is removed, and the energy now also depends on mj quantum number. This effect is known as Zeeman effect when the applied field is magnetic, and Stark effect if the applied field is electric. So let us summarize whatever we have learned for polyatomic molecules. Linear molecules exhibit rotational spectra in which the spacing between adjacent lines is 2b, from which the moment of inertia and the bond length of a diatomic molecule can be extracted. However, for polyatomic molecules, there is more than one bond length to be determined, and only one rotational constant that can be obtained. The technique of isotopic substitution is employed to determine all the bond lengths. Spherical top molecules do not possess a dipole moment and are hence microwave inactive. In symmetric top molecules, another quantum number k is involved. For correlated symmetric top molecules, each energy level is raised by an amount that is proportional to k square. But in oblate top molecules, there is a lowering of energy levels. However, since the selection rule for k is del k equals 0, the spectra still resemble those of linear molecules with equal spacing, though each line now is a superimposition of many lines. The dipole moments of linear and symmetric top molecules are accurately determined by determination of the splitting in the presence of electric field, what we call this as Stark effect.